transmit the genes to all daughters because the X chromosome is passed on to the daughter from the father, and it's the Y chromosome that goes to the son. And so fathers do not pass on any of the genes on the X chromosome to the sons. The daughters of affected males will be heterozygous unless, of course, the mother also passes on the affected allele. And the sons of heterozygous females have a 50% chance of being affected because they will receive the affected gene. Heterozygous female, 50% chance of receiving the recessive gene. So you can see a kind of schematic pedigree of an X-linked trait. And you can see how the affected gene is noted. Here is a male, got a single copy of this affected gene, and because they are hemizygous, that male is affected. That male will pass on that affected gene to the daughters. Every daughter will get that affected gene. But since the mother is homozygous normal, the daughters are not affected. But then the daughters will pass on that gene to the sons at a 50% rate. And because they pass it on at a 50% rate, the sons will be affected. And so, because of these rules, a gene on the X chromosome is more often going to be observed in males. So males are going to be more affected than females. So it's a recessive trait. So two unaffected parents will produce affected children. That's the first thing you should know. And then when you look at the entire pedigree, you will see that most of the affected individuals are males, not females. Now, there might be an occasional single female that might be affected, obviously. But it's very rare. Well, not very rare, but it's rare. Let's put it that way. Most of the time, it's the sons that are affected with a gene on the X chromosome. All right. So, males get their X from the mother. Fathers pass their X to the daughters. Females will only express it when they get a copy from both parents. And it is expressed in males if it is present because they have a single copy. So, here is a male, X little r with the Y chromosome, and a female, that's wild type, X big R, X big R. Obviously, this female will be heterozygous by definition because of the big R coming from the mother and the little r from the father. The son will be wild type, X big R and Y. Now, if they mate, here is the father, the husband. Let's imagine this male here is affected. Because they're affected, they will be X little r and Y. Let's imagine this female is also affected. Because this female is affected, her genotype will be X little r, X little r. So now you can calculate the probabilities of these individuals being affected. Correct? So what's the probability of this male being affected? 50%. Correct. Half probability, because there's a 50% chance of getting this X little r chromosome, 50% chance of getting the X big R chromosome, right? And so, because the X chromosome to the son always comes from the mother. Okay, what about this daughter here? What is her probability of being affected?
Quarter.
Again, it'll be 50%. Why 50%? She's going to get the X little r chromosome from the father, but then she also has to get the X little r chromosome from the mother, and there's only a 50% probability of getting this chromosome from the mother, and so it's going to be a 50% probability of being affected. What about this son? What's the probability of this son being affected? 100%, correct. So probability of the son being affected will be 100% because this mother here is homozygous recessive. And what's the probability of this daughter being affected? 0. Because she will get the X big R chromosome from the father, right? Yes? So the key when you're starting to work on probabilities and pedigrees, the first thing you guys should do is try and write down the genotypes of the parents and the grandparents. So once you've written down as much of these genotypes as you can, then you can calculate the probabilities of the progeny that I'm asking about. Okay? So the first step in this is always to try and figure out the genotypes, as with all the information I've given you and what you kind of figure out. So now let's look at genes on the Y chromosome. How is the Y chromosome passed on? Basically, the Y chromosome is always passed on from the grandfather to the father to the grandson. The Y chromosome only follows the male lineage, so it's always passed on in this general way. Daughters have no effects, mothers have no effects. It's always the male lineage, basically. So all males in the pedigree will have the same Y chromosome. There's almost no recombination on the Y chromosome. So imagine a grandfather, this grandfather here, has an X chromosome, let's call it X1, and the Y chromosome, let's call it Y1. Okay? We'll ignore the autosomes, A1 and A2. Forget about the autosomes, not important. This grandfather mates with his grandmother. This grandmother has X chromosomes, let's call them X2 and X3. Okay? Now you have the son here. The son might get this X2 chromosome from the grandmother, and he will get the Y1 chromosome from the grandfather. Correct? Okay. Now this father here mates with this woman, and let's give her X chromosomes some numbers, 4 and 5. Okay? And now they're going to mate, and they're going to have a daughter and a son. This daughter might get the X5 chromosome from the mother, right here, and might get the X2 chromosome, and will get the X2 chromosome from the father. Okay? But look at this grandson here. He will get the Y1 chromosome from the father, and then he might get an X4 chromosome from the mother. So note what happened to the Y chromosome. There's the Y1 chromosome in the grandfather. The father also had only the Y1 chromosome. The son also had the Y1 chromosome. So the Y chromosome doesn't change as it goes on from grandparents to parents to grandson to great-grandsons, and so on and so on. And so you can use that to study pedigrees across many, many, many generations. And you can use that to study migration, because the only way the Y chromosome varies from one individual to the next is by mutations that are introduced at random into the chromosome. And so when two individuals have very similar Y chromosomes, they must be very closely related. And two individuals whose Y chromosomes have diverged a little bit because of random mutations that occur because of the environment, they would be further away from each other in a pedigree. And so using that analysis, you can actually analyze how humans have migrated. Because humans, until the modern world, they didn't travel very much. They traveled basically along land and rarely on the sea. And so they all were related to one another based on geography. And so you can actually follow through analyzing the Y chromosome and looking at human migrations. And the theory is that humans migrated out of Africa, and then they migrated in these places. There is a really wonderful story about using the Y chromosome. It's a tribe in Africa called the Lemba. And they claim to be one of the lost tribes of Israel. And they basically practice circumcision, you avoid eating pork or pork-like animals, and they basically claim they are of Jewish heritage. For the longest time, people didn't believe this, until in the 1990s, they started sequencing and analyzing parts of the Y chromosome. And they basically discovered that the Kohanim priests in the Jewish ancestry have a very specific sequence on the part of the Y chromosome, very characteristic. Okay? That's very rare in non-Jewish populations, but present in this population. And so a team of geneticists went to the Lemba in Africa and sequenced their Y chromosome, or at those regions of the Y chromosome, and lo and behold, sure enough, they had the same characteristic pattern as the Kohanim priests, basically. Now, whether that proves or disproves that they are of Jewish heritage is a different issue. But based on the sequencing, it seems that they are related. So you can use this quite often. You probably heard of another example, that Jefferson fathered Sally Hemings' son, correct? You've all heard about this. The way that was also done was by sequencing the Y chromosome. So here's a classic example of scientists kind of stating more than they actually should. This is something you guys should remember. Even scientists are human. They like to kind of boast a little occasionally. This is a paper in Science, one of the premier journals in science. And here's the title: Jefferson Fathered Slave's Last Child. Very definitive title. Then you should look at the data. So what was the data? So where's Thomas Jefferson? Here's Thomas Jefferson. You notice Thomas Jefferson doesn't have any children. So how did they study the Y chromosome of Thomas Jefferson? Well, they studied it along his brother's lineage, Field Jefferson, right here. And these are his progeny, and it's their progeny, his progeny, I've shown them over here, that they analyzed the Y chromosome in. And then they backtraced it down, and they said, since the markers of Sally Hemings' son looks almost identical to the markers on Field Jefferson's children, it must be that Sally Hemings had a son with Thomas Jefferson. Now, it's very likely that's the case, but it doesn't prove it, right? The title of this should not have been as definitive as it was written. So when you read something in a newspaper and they say scientists show this, be skeptical. Ask questions, okay? Don't just accept things because people tell you that's what it is. And I'd like to put this up as a prime example of that. All right, so now we're going to look at more detailed analysis of certain pedigrees, just so that you get used to calculating pedigrees and things of that nature. So, we're going to only look at a few simple things. We're going to calculate the pattern of inheritance. We're going to determine the genotypes of individuals, and then we're going to determine the probability of offspring that might arise in the future. Three things we're going to do, looking at a pedigree. Okay? So, we've gone through these markers. I'm going to skip over these. They're pretty much the same things we talked about earlier. Let's assign some genotypes. Okay? So we're going to look at autosomal recessive pedigrees. So the first thing with an autosomal recessive pedigree is an affected individual. Correct? An affected individual in an autosomal. If you look at this pedigree, do you see it to be recessive or dominant? First question. That's the first thing you have to ask yourself. You analyze a pedigree, forget about these nomenclatures. Let's imagine you don't have this genotype written out. If you don't have the genotype written and you just are given this pedigree and you analyze it, what would you tell me? Is it recessive or dominant? Recessive. Recessive. Why? Because two unaffected individuals are having affected children. Is it X-linked or autosomal? Autosomal. The reason? Approximately equal numbers of males and females are affected. So now you have a basis. You know it's an autosomal recessive pedigree. Once you know it's recessive and autosomal, you can start filling in the details. You can definitely write down the complete genotype of this individual. Because it's recessive and she's affected, it will be little a, little a. Little a being affected, mutant allele, big A being the wild type allele. And the same thing here, and the same thing here, and the same thing here, and here, and here. All right. Then you start asking yourself a question. Okay. You fill in all the unaffected individuals with one big A. You know they have one big A because that's why they're not affected. Correct? But you can't fill in the second one because they could be homozygous dominant or heterozygous. Correct? So you leave a dash. Then you ask yourself, okay, now here's the rule. Two unaffected individuals are producing an affected individual, so the unaffected individuals must be heterozygous. Correct? So you can fill in this pedigree here and this one here. Similarly, you can basically look at this generation, and you can say, okay, this small a has to have been given to all 3 children. Correct? So you can fill in little a, and little a. Now remember the outsider rules. I have to give you the genotypes of the outsiders. They come into the pedigree from outside. In this class, we don't follow any rules. I will give you this information, and so I've given you that information. Based on that information, you should be able to figure out what's going on. So you can't fill out the entire genotype of every individual in a pedigree, but you can fill out the significant number of genotypes in this pedigree, right? And so that's how you would do this analysis. You follow the simple rules, but the first thing to do is figure out if it is recessive or dominant, and if it is autosomal or X-linked. Once you figure it out, then start filling in the pedigrees, basically. Okay, here is another example. Okay, again, recessive or dominant? Recessive or dominant? How many think it's recessive? How many think it's dominant? Recessive. Let's put your hands up for recessive. Okay. Dominant. Very few dominant. It's recessive. 2 unaffected individuals having affected children. So it has to be recessive. Is it X-linked or?
But what about the one on the right side?
This one?
Because the affected parents having unaffected
They're
children.
not having affected children. They're having unaffected children. Dominant mutation. If the father or the mother is affected, it's very likely that half of the progeny will be affected. Right? Because they have 2 copies, one big A, one little a. Let's imagine this father is big A, little a. And big A is the mutant allele, dominant mutation. Correct? Then, and they have 4 children, approximately half of the children would get the affected allele. Right? So, second reason why that couldn't be. Okay, so we've assumed it's recessive. It looks like it might not be sex-linked because you have males and you have females, correct? So now you go with that assumption that you are most likely autosomal recessive. And now let's try and work our way through the genotypes. So all the affected individuals will be little a, little a. So you write those down first, correct? Okay, now you've done that. Then you go to the next step. All unaffected individuals will have at least 1 dominant normal allele. So you write down big A, 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 big A. Correct? 1 allele. Then you write down recessives must get 1 recessive allele from each parent. Correct? So here is a recessive. So they must get a recessive allele from the parent. So there's your little a and little a. You fill that in. Here is another recessive. So they must receive a little a and little a. So these 2 parents get written up. Right? And then all of the offspring of a homozygous recessive must have at least 1 recessive allele. Right? So here is a homozygous parent. And so they must have given a little a to all of these individuals here. Right? So you can fill in this gap. And then questions.
Why were you able to say that's not sexually so quickly? Because like,
Well, in this example, it's females who are being affected more than males. So how do you do that if it's sex-linked? And it's recessive, not dominant. Right? And then so the last thing you do is for the rest of the genes you will use a dash to basically say that the second allele is unknown. So for example here you put a dash saying I don't know what that is, here, here, and here. And there you have your entire pedigree. So simple logical steps you use to kind of fill out the pedigree.
Question?
Yes?
What is the difference between the split that is coming from the same point and the
these
one
are-
that are branching above it?
These are twins.
Are they the same as the branching from the same point below? Is there a difference?
These are non-identical twins. These are identical twins, and there's a slight mistake here. There should have been a little dash over here.
Okay.
But in this example, the way I've written out twins is basically you start with a single point and then branch it. That's one other way of which you can have a pedigree with identical twins, basically. Here you have non-identical twins, and so you don't have that little line dropping down. But I'll try and be consistent. In the original symbols on my page, I had a different way of showing identical twins versus non-identical twins. So in the exams, I'll make sure if there are twins, I'll use the one that was originally proposed. Hold on. So I'll use this to show identical twins, this to show non-identical. They have that single line, but they also have this little connecting line. And I'll make sure that the connecting line is there when I'm talking about identical twins versus non-identical. All right? Somebody had a question? Yes, question.
For the grandparent, can you say that on the left side, can you say that the female is heterozygous because 100% of their offspring are heterozygous?
So the female would be homozygous. It's likely, but you can't be 100% sure, but yes, it's likely. You could definitely say this is big A, because we've given you 4 different examples and they're all 4 big A's. So yes, you could in theory write that.
So
Absolutely.
if that was like a question and we were to put there's homozygous on it, but it's not 100% sure what that means.
I try not to ask questions that are so ambiguous, basically. But yes, you could definitely, because there are all 4 individuals here, and all 4 individuals are big A, it's very likely that this individual is big A. You're absolutely right.
Question.
Yes?
How come you know the son for the second set is big A, little a?
This one?
Yeah.
Because there are 2 unaffected
Oh.
parents producing affected progeny. All right. So, again, these are the rules for dominant pedigrees. You've seen those rules before already. In dominant pedigrees, you basically will also try and fill things in. Notice for dominant pedigrees, every generation has an affected individual. An affected child will have an affected parent, basically. Has to. Correct? Irrespective whether it's sex-linked or autosomal. And so you will always have a connection between them across generations. And every unaffected child or individual will be little a, little a. Right? So you can fill in all the unaffected ones first, very quickly. And for the affected ones, you can fill in the big A, and then you leave a gap, a dash, unless you're absolutely sure about it. And the way you're absolutely sure about it is, for example, look over here. Okay? You have 2 affected individuals producing an unaffected child. If it's a dominant pedigree, how do you get an unaffected child? Parents have to be heterozygous. And so you can fill in big A, little a, or big A, little a. Similarly here, if it's a dominant pedigree, this parent cannot be big A, big A. If they were big A, all 4 children would be affected. And because they're not, this parent will be heterozygous, big A, little a. Right? So, simple rules of dominance and recessive, that's all you have to kind of pay attention to. And then once you know that, you should be able to fill in most of the pedigree. You can't fill in all of the pedigree, very rarely can you do that. Of course, sometimes you can, but most of the time you can fill in the majority of the pedigree using these simple rules. I'm just showing you these. There are lots of homework, not lots. I've given you several homework problems with stuff like this so that you can practice and figure out how to work on these things. I'm just showing this to you. Okay, so now let's do some calculations again. Okay, I did one calculation previously. I'm going to give you a couple more calculations now so that you get more familiar with calculating probability. Okay, so here is a cross. Okay, It's an autosomal dominant trait. I'm just giving it to you right now. If the pedigree was large, you could have figured out it's an autosomal dominant trait. Let's say here is the pedigree, the important one. And I want you to calculate the probability of this individual being affected. So I want you to determine all the parents' genotypes and then determine the frequency of the mutant phenotype. Okay, so I've given you the pedigree or the genotypes of these two parents. This parent is little d, little d. All right, unaffected, it's a dominant trait, so there. Now this parent is big D and a dash. We don't know if the second allele is big D or little d. So we don't know if it's homozygous dominant or heterozygous dominant in the mother. So you basically have two possibilities. You have a 50% chance that she is big D, and 50% chance that she is big D, little d. So what is the probability that the child will be affected? So father's probability is, there's only a single probability of the father, and the father is only going to be little d, little d. Mother has a 50% chance of being big D, and 50% chance of being big D, little d. Right? Okay. Now this is an autosomal dominant pedigree. So determine the probability of an affected child. That's the question I've asked you. So what do you think it is? This is a simple answer. So what's the answer? What do you think is the answer? Just off the top of your head, what do you think it is?
3/4.
Somebody said 1/4.
3/4.
3/4. Okay, excellent. All right, so let's calculate this. What you have to basically do is you have to calculate the probability for each set of parental genotypes, right? And then you add the two, all of them together. So how many different ways in which you can produce a child in this cross? How many different types of possible types of matings can there be? 1, 2, 4, 6, 2. You will have a little d father crossing to a big D mother, or you have a little d father crossing to a big D, little d mother. So two possible crosses. And then you're going to combine them. Okay. So here it is, mom has a 50% chance of this and this, followed by dad who's only little d. So there are two possible cases for the cross. Big D cross to little d, or big D cross to little d. Okay, now if the cross is big D cross to little d, all of the offspring will be big D, little d, correct? So 100% probability of the cross or the progeny being affected, right? Fair enough? Okay, so this is 1/2 is the cross, and the probability of the progeny being affected is 100%. So, on the other hand, if the cross is big D with little d, only half of the offspring are big D, little d. Correct? So in the second cross, the probability of the second cross is 50%. The probability of an affected offspring from that cross is 50%. Right? So you can do the calculations. Big D with little d, 50% probability of having this cross with all offspring being affected. And the probability of mating between big D and little d is 50%, with 50% of the offspring being affected. So that's 1/2 plus 1/4 equals overall. Right? So that's how you basically will calculate them. The key in calculating conditional probabilities is figuring out all the different ways in which you can generate that progeny. That's the issue. Very often you will miss one. And if you miss one, and if you're unlucky and the answer, then you will get a wrong answer. So you have to stop and think how many different ways you can generate the progeny. And that's why it's very important to try and figure out the genotypes of the parents before you start your calculation. All the different genotypes of the parents. I'm giving you another one. This is an autosomal recessive. Here is the the pedigree. A little bit more complicated this time. Correct? Notice how this works. This father has two probable genotypes. 50% big R, 50% big R, little r. This mother has two probable genotypes, but those genotypes are different. It's 1/3 big R, and 2/3 big R, little r. This is an autosomal recessive pedigree.